Hi, this is Gordon Parker from Michigan Tech, and in this video I'm going to go through a lead compensator design using Locus. We'll do it all by hand first and then switch over to MATLAB. So here's the plant that we'll be working with. Pretty simple one. Second order with some complex poles. And those poles are at, let's see, S1 and 2 and -1 plus minus 2j. And I guess before we get started we should look at the block diagram of this. We have a compensator D of S. Here's the plant G of S. And our old unity feedback and a reference input R and an output Y. What we'll do first is we'll just let D, the compensator, equal a proportional controller K. And just play around with it a little bit and get familiar with it. Well, first we can see with this unity feedback system, in D just equal to K and G, second order with no poles at the origin, we can conclude that this is a type 0 system. So if I give it a step reference input, I'll have a constant steady state error. And we can actually calculate that steady state error by noting that the position error constant is the limit as S goes to 0 of D times G, everything in the forward path. And so in that case, we would have 2.5k over 5. And then the steady state error for a unit step input would be 1 over 1 plus kp. So what we can see here is that as I increase k, I can drive down the steady state error. Oh, and this goes all the way over. But I still will have a finite steady state error, and it's not 0. Let's see, from a root locus perspective, one thing that we typically need to do is to note the loop transfer function, which in this case is exactly the same as the plant, and jot down the number of zeros and poles. So m, the number of zeros, is 0, and n, the number of poles, is 2. What this tells us is that we have two asymptotes. I'll just abbreviate it like that, and their angles are at plus minus 90 degrees with respect to the real axis. So I have vertical asymptotes. Then the other thing we can do is calculate the point where the asymptotes intersect the real axis. There's many ways to do that. One way to do it is to form the characteristic equation, which would be 1 plus k GL equals 0. And I can just work this out a little bit. CS squared plus 2s plus 5 equals 0. And so now it all starts taking shape. Now let's find the point sigma where the asymptotes intersect the real axis. And the way we do that is we take the coefficient of the second highest power in S of all the stuff that multiplies k. Well, that's just 0, because there is only one coefficient that is multiplied by a power of S, that's S to the 0, and there is no second highest power of S. Over here, though, we do have one. It's 2. So I have 0 minus 2 divided by n minus m, which is also 2. So I have an asymptote at -1. Now I can actually sketch this root locus. I have asymptotes at plus minus 90. They intersect the real axis at -1. And the k equals 0 points, which are right here, are like so. So let's just do that. Just a very crude sketch to get the sense of this. Let's see. Okay, so -1 plus minus 2j. This is where our k equals 0 points are. The asymptotes are at plus minus 90 degrees, and they go right through the point -1. So guess what? The root locus just zooms off from those k equals 0 points into the complex plane. Well, that's interesting. What it tells me is that as k goes up, the damping ratio of these two poles is going to go down, and that means that the percent overshoot is going to go up. Another thing that happens as k goes up is that omega n, which I can interpret as semicircles in the complex plane with constant radius, is going to go up. And so the speed of the response is going to also go up. That means that things like the rise time is going to go down. So the response gets faster. That could be a beneficial thing. So now let's go ahead and do a lead compensator design. And the goal is going to be to try to keep the percent overshoot about what it is now. And so the way I'll approach that is trying to keep zeta approximately what it is right now, but achieve some faster response, increase omega n. I can't do that now because if I tried to increase omega n, my zeta would go down. The way we can see that, by the way, is that if I draw a line from any point on this root locus to the origin, this angle, I'll call it theta, is related to zeta. Sine theta is equal to zeta. And so as the pole goes up, theta gets smaller and zeta gets smaller. So before we do the lead compensator design, let's just look at this root locus in MATLAB. Here's the loop transfer function. I'll use the TF command, put in 2.5125, and let's use rltool to explore this root locus a little bit. Great, so there's a beautiful looking root locus, and under analysis we'll look at the response to a step command. Now that shows the blue is the response to the step command. If I right click on here in systems, I can see that the green is the reference input to the plant, and I'll click that off. We don't really need to see that. If I right click over there some more, I can pick some characteristics. The peak response, the rise time. Those are a couple that we're interested in. So if I hover over the peak response, I can see that the overshoot's about roughly 30%. And if I look here, the 0.1 to 0.9 rise time is roughly half a second. So what we'll do is, with the lead compensation, is try to increase the rise time without hurting our percent overshoot too much. But the main focus is going to be to get the response to be faster. So let's just jot down what we learned from using rltool. For k equal 1, we had a rise time of about half a second, and the percent overshoot was about 30%. Okay, so now let's take a look at the lead compensator. The lead compensator has this form. D of s is going to be k s plus z over s plus p. And so the lead compensator design process is the act of finding k, z, and p. Now the lead compensator has the absolute value of z less than p in the complex plane. What that means is that the zero of the lead compensator is closer to the imaginary axis than the pole. So it looks like that. Now if we look at our loop transfer function with the lead compensator in it, we have 2.5 s plus z over s plus p and s squared plus 2s plus 5. And we can jot down the number of poles, which is 3. The number of zeros is 1. But what's interesting is n minus m, that's an m, is still equal to 2, which means there's 2 asymptotes, and they're at plus minus 90 degrees, just like we had before. However, now the location of the intersection point of the asymptotes with the real axis is probably going to change. The way we can look at that is to form the characteristic equation, which is 1 plus kgl, and that will be s plus p, s squared plus 2s plus 5, plus 2.5k, s plus 2 equals 0. And now we'll multiply that out, so we get s cubed plus 2 plus ps squared plus 5 plus 2ps 2.5k S plus Z equals 0. So a fair amount of algebra just to find this and this. So sigma is equal to Z, that's this thing, minus the quantity 2 plus P over 2. Great, that's N minus M. If I rewrite this, perhaps it's a little bit more instructive. I could write it as minus 2 minus P minus Z over 2. Now, the intersection point that we had before was just this. What I can see now is that I'm going to move it to the left to the tune of P minus Z. So if I sketch this briefly, what will happen is, if these are the poles of the original plant, and now I add this lead compensator in there, the asymptotes are going to move over. I'll just stick them here, even though I don't exactly know where they'll be. They'll go over there. So instead of the root locus going up like so I'll cross those off, it's going to go like that. Notice what this lets me do is I can increase omega n. Right? This is increasing omega n as the circles have larger and larger radii. But my zeta, which has to do with these lines, could be still kept relatively low as omega n is increasing. So an interesting design feature. Let's just look at one more thing before we actually go through the design. Remember that what we had before for steady state error was, this is for the old case, proportional control. We had steady state error was 1 over 1 plus Kp. Well, that's always true. But Kp was equal to 2.5 K over 5. Now let's look at what happens with the lead compensator. Steady state error is the same, but Kp, which is the limit, as s goes to 0 of dg, is now equal to 2.5 K, the location of the 0, z, over 5p. And p is larger than z. Right? This distance is larger than that distance. So when you put this value of Kp into here, the steady state error is actually going to go up. So while our lead compensator allows us to increase the speed of the response with keeping the damping relatively the same for this example, the steady state error is going to get a little bit worse. Just something to be aware of. Another thing to be aware of, if you look at this messy sketch right here, is that as these poles are heading off like so, this closed loop pole is heading to this k equals infinity point. The impact of that is that these poles may no longer be dominant. That is, this pole may be sufficiently close to these poles such that I can't just always use the second order time domain type relationships to do the design. The implication for what we're doing is that if I keep the zeta the same for the lead compensator design as I had for the proportional control, I may not actually get the percent overshoot that I was hoping for. I may have to be a little bit more aggressive with my zeta, that is making it larger, to keep the percent overshoot down. But we won't get into that nuance just yet. We'll just try to keep the zeta about the same that we had for the proportional controller and see where it takes us. So now let's do the design. One more sketch. Here's the k equals 0 points for the root locus. These are at -1 plus minus 2j. So let's increase omega n but keep the damping ratio the same. So I'll draw a line of constant damping ratio like so. And let's go for closed loop poles that are at -2.5 plus minus 5j. So I've multiplied both of those by 2.5. So I know I'll have the exact same damping ratio. Now what happens with the lead compensator is I plug a 0 and a pole in there, and what I'm going to do is use these two quantities to add phase to the loop transfer function so that my root locus will go through this point. It'll actually bend this root locus from going up like so, it'll bend it around like this. So the question is, how much phase do I need? I better go to another page that I have some clean paper to work with. So for a root locus, we know that any point on the root locus, S0, the phase of the loop transfer function has to equal negative 180 degrees. So let's carefully draw this. And what do we have? Let's see. We have negative 1 plus 2j, negative 1 minus 2j. And we're going to put the closed loop poles at negative 2.5, right about here, plus minus 5j. 1, 2, 3, 4, 5, right about here. And I can see that I maintained the zeta approximately the same. Now, we're going to call this point S0 and draw some lines to it from the poles that we have of our plant. And I'll label those phi P1 and phi P2. Great. Now what I'll do is I'll take this equation and note that what it means is that the sum I equals 1 to m of the phase of all the zeros minus the sum I equal 1 to n, the phase of all the poles, plus a yet to be determined phase lead equals negative 180. And what I'll do is calculate the phase associated with everything that isn't the compensator, so in this case it would be the plant, and then calculate how much lead I need, how much phase lead I need from the lead compensator in order to force this condition and the poles to be at this point. Sounds crazy, but it's really not that bad. So if I look at this piece first, that's the phase associated with these two poles. So there is no phase associated with this, with any zeros. And now for the poles, I'll have, let's see, if I do this one in two pieces, I'll have 90 plus the inverse tangent of 1.5 over 3. And then I have another piece, which is 90 from here to here, plus the inverse tangent of 1.5 over 7. Well, this is roughly 26.6. This is about 12.1. So, oh, and I don't want to forget this, so I have plus the phase lead from the compensator equals negative 180. I get some nice cancellation here, and I can solve for the phase lead that I need from the compensator, and I'll have 26.6 plus 12.1. So what I need is 38.7 degrees. Beautiful. Now, how to get it? So, let's go to another page, and I'll redraw just a piece of this. Now, we have the original poles at negative 1 plus minus 2j. We have this point at negative 2.55. About there. One way that I can get this phase lead of 38.7 degrees is to stick the 0 of the compensator right there. The reason I'm doing that is just because it's easy, because that gives me 90 degrees of phase lead. And now I need to have a pole someplace such that this angle is 38.7 degrees. So what that means, let's see, let's define this as delta. Let's define this distance as delta and go ahead and solve for it. So the tangent of 38.7 is equal to delta over 5. So that says that delta is just 4. Well, that's pretty easy. So I didn't draw it quite to scale on here, but it means that my pole should be at, if this is 2.5, should be at 6.5. 1, 2, 3, 4, 5, 6.5 right here. So now my compensator is D equals K, S plus 2.5 over S plus 6.5. The only thing I now have to do, and I'll get rid of this line, the only thing I now have to do is figure out what the value of K is. Now to get to that, I have to remember that my loop transfer function is equal to 2.5K S plus 2.5, that's an interesting coincidence, over S plus 6.5 S squared plus 2S plus 5. And then draw arrows up to my desired pole location. I'll get rid of this line too. Actually, I'll get rid of this angle. And use this equation. The magnitude of GL is equal to 1 over K. And the magnitude of GL is the magnitude of all the zeros up to this point, divided by the product of the magnitude of all the poles up to that point. And so if I do that, so I'll have 2.5 from this. This term is associated with this 0, and the length of this arrow is 5. So I'll have a 5 up there. Divided by, let's see, so I'll go after this term. So the length of this arrow is the square root of 4 squared, so that would be 16, plus 25. Then if I go after this term in 2 pieces, so if I do this one first, I'll have the square root of 3 squared, which is 9, plus this distance squared, which is 1.5 squared. And the last one associated with that pole is the square root of, let's see, this quantity squared, which is 7 squared, 49, plus again 1.5 squared. And if I calculate that out, and then note that I have to flip it to get K, I'll get K equals 12.4. So now I have the whole compensator. Now let's look at this process using rltool. Let's code up the plant, 2.5125, and use rltool to investigate this a little bit. So here's our old friend, this root locus, and now what we'll do is go into the Compensator Editor, right click here, add pole 0, but actually what I'll do is choose the lead option. It gives some nominal values for the real 0 and real pole, but we'll change those to our values, 2.5 and 6.5, and look at the wonderful things it does to the root locus plot. We'll throw a grid on it, and let's just go ahead and grab this point and drag it over until we get the closed loop poles that we were trying to get. Just basically -2.5 and 5. There we go. And what else should we do? How about, under analysis, we'll look at the response to a step command. Right click in here for systems, let's get rid of the green line, and then show some of the characteristics, peak response and the rise time. If we hover over the rise time, we see that it is now 0.2 and it used to be 0.5 for the proportional controller. So that's a win. If we look at the peak overshoot, it's now closer to 38%. We had 30% before. So we have quite a bit more peak overshoot. And the reason for that is that our closed loop poles, this complex pair, is no longer actually dominant compared to the other complex pole, which is right here. So if we really had to get the lower percent overshoot, we'd have to adjust our design a bit so that our damping ratio is more aggressive than the 0.44 or so that we have right now. We can see that by just hovering over that pink, clicking on the pink line, and we can see that the damping ratio is about 0.4 or 5 actually. Now the last thing that we're going to do is just take a peek at the gain that this rltool came up with. It's 4.7, but we had 12.3. And why is that? It's because the compensator form is a little bit different. They've actually divided through by this 2.5 and 6.5. So if we want to just do a quick comparison to our gain, we could take 4.72 and multiply it by 6.5 and divide it by 2.5. And we get roughly 12.3, which is what we calculated. Great. So just to summarize, we started out with looking at a very simple plant that just has a couple complex poles. Looked at a proportional controller and the ramifications of increasing K. And then postulated a lead compensator for trying to keep the damping ratio the same but increasing the speed of the response. We're able to design that all by hand and then check it with the rltool. The percent overshoot went up a little bit because the complex pole pair that we ended up with was no longer dominant, and if we really had to get that percent overshoot, we could. Well, again, this is Gordon Parker from Michigan Tech, and thanks for watching.